everyone. In the last video, I covered permutation and combination, and today's topic is classical, frequentist, and Bayesian probabilities. So let's begin. So, Kolmogorov axioms define what probability must satisfy, not what probability actually means. So, there are three competing interpretations assign meaning to probability of any event. These are classical, frequentist, and subjective. Classical is like classical counts symmetrical outcomes. Frequentist is for long run relative frequencies, and Bayesian is for degree of rational belief. Okay, all three are like axiom compliant, means they have to follow Kolmogorov axiom. Next, moving on forward, the core paradox of probability. Okay, this I covered. Next is like classical probability. What is it? It just requires fine a sample space which is finite and all outcomes are equally likely. This is circular if equally likely is defined using probability. The definition assumes what it's trying to define. Okay, it works good for dice, cards, where coins, these kind of questions. And how you read the formula is like number of favorable outcomes upon total number of equally likely outcomes. Moving on forward, there is one topic like frequentist probability. Now, what it is? Probability is a property of repeatable processes, not a single event. So, it requires experiment which can be repeated infinitely under identical conditions. And here, this in the formula, you can see f of n is written. F of n means number of time e occurs in a n repetition of the experiment. Okay, so let's see, like if there is probability, it's range tomorrow. This is meaningless because tomorrow is not repeatable, right? And what if it's has like probability that this specific patient will recover or not? So this is also meaningless because one patient will have one outcome only, like that. So only well-defined of random processes with stable long-run frequencies are needed in this frequentist probability. Okay. Next comes subjective and Bayesian probability. Now, in this, it is all about your rational belief, your rational degree of belief that event occurs. Okay, for example, it must still satisfy, first of all, Kolmogorov axioms. Otherwise, this can't be performed. Okay, and it always allows probability statement about one of one events and parameters and hypothesis. Okay, moving on forward, the fair coin. Okay, how you see a fair coin toss in different of the things like classical, frequentist, and Bayesian. You can see it here. Moving on forward, the next selection. Yeah, so it's all like that. Okay, here's the comparison table which we need to understand. So for how probability is defined in classical, it's all about symmetry, equally likelihood. And in frequentist, it's like long run frequency. Whereas in Bayesian, it requires the degree of belief. Okay, what are the requirements for this kind classical frequentist and Bayesian? For classical, it's equally likelihood event should occur. Then for frequentist, repeatedly a event should occur. And for Bayesian, there should be prior belief needed. Okay, okay. So now probability of a parameter. In the classical, it's meaningless. In frequentist, it's meaningless. But in Bayesian, it's valid. Okay. Now, um, what is the objective of class? No, wait a second. Hmm. Updates with data. Okay, out of these three, which updates with data? Classical won't update, frequentist won't update, but Bayesian will update. Okay, and here only Bayes theorem we will study in future. Now moving on forward, it's just a question you can. No, it's a pitfall. Okay, pitfall means like where we can make mistakes. So let me tell you, like equally likely is an assumption, not a derivation. So classical probability does not justify why outcomes are equally likely. It just assumes it. For a loaded die, classical probability is wrong from the start. Okay. Next thing is like frequentist probability of a fixed parameter is undefined. In frequency statistics, theta, like a model parameter, is a fixed, unknown, not random. Okay, so probability of theta greater than zero is meaningless frequentistically. So this is why frequentist confidence intervals are widely misinterpreted. This we will study in future topic. Okay. Next is Bayesian is not equal to subjective in a sense, like the prior must still be coherent, and means it should satisfy the axiom, and it encodes actual prior information, not arbitrary opinion. Okay, with enough data priors wash out anyway. Okay, next is like all three can give different answers on the same. So what it means, like when there's example, like there's something Bertrand's paradox, asking like random chord of a circle. So it gives different classical probabilities depending on what you defined as symmetric sample space. Okay. So now in ML, in ML also we make a mistake, like most of us mix interpretation without realizing it. Maximum likelihood estimation is frequentist. Putting a prior on weight, like L2 regularization is equals to Gaussian prior, is Bayesian. Okay, knowing which framework you are in matters for the interpretation. So remember it. Now why we are studying it? What is the ML connection with it? So the split is like foundational to machine learning. Frequent is mean loss error and hypothesis testing, p-values, confidence intervals, and Bayesian is used in MAP estimation, posterior inference, and Bayesian neural nets, probabilistic programming, Gen AI models may we use like diffusion, VAs use Bayesian reasoning explicitly. So this is the very important topic to understand. So I tried my best to explain this topic from my side. If you find any mistake, you can just tell me. Bye bye.